So, shall we get started? Okay, so I think that we're at the end of week 4, I believe, now. So we are very much in the meat of the course. So hopefully today will be a little bit more of a no new stuff lecture, and we're just going to review things that we already know. But it's probably a good time to take a look at the schedule for everybody. As you know, assignment 2 is out. Hopefully most of you have at least kind of really sunk your teeth into at least parts 1 and 2, and if you're not really soon getting on to part 3, the real assignment is part 3. So I hope that you're at least starting to look at part 3. We have a recitation this evening in this room at 7 p.m. It will not be filmed, and the recitation will cover sort of some key ideas of CUDA programming. How to use shared memory if you want to, how to make efficient access to memory. So I don't believe Professor Bryant is going to specifically talk about the details of assignment 2, but I think a lot of the concepts that we're going to talk, or that he'll talk about in that recitation, absolutely will be very helpful in assignment 2. Question? No? Okay. And then I also kind of want to look forward a little bit. Is that so assignment 2 is due next Wednesday. We immediately go into assignment 3 the next day. So we've been talking a lot about characteristics of hardware, how to think about the basics of parallel programming. Today, like I said, I'm just going to start throwing out some examples, and we'll just talk about some of the examples to get more and more experience with parallel programming. Next Monday will be a lecture on thinking about how to analyze performance. And then we're going to move into something completely different. We're going to move into how modern hardware implement some of the details that we've been assuming. Like, for example, if we have a bunch of processors sharing the same memory, how do we coordinate access to that memory and things like that? And so those hardware details will take us to exam 1. So exam 1 in this class is often a little rough on some people. So we're trying to do a better job this year of forcing you to kind of, through the exercises, through some of these recitations. I'll have another recitation on Sunday that I want people to start thinking of as like exam review sessions, so we can start hitting some of the ideas now and not hit those ideas 48 hours before the exam. Okay? So exam 1 coming up. Assignment 3 is actually outstanding over the exam. I mean, we give you a fair amount of time on assignment 3, but you have to manage yourself, because there'll be a period of those 2 or 2.5 weeks where you probably should be spending time on the exam and not on anything else. So any other questions about sort of where we're going, why, what you should be thinking about? Yes? No? Where everybody's good? Okay. Access to TAs is going okay? No major complaints? Maybe we can do a little survey later in the week to figure out if there's anything we need to change. Okay, so let's review a little bit. I always like to start the class with something from last time. And last time, I ended very near this program here. And this is something that will come up many, many times in this class. And I said, hey, you NumPy folks, NumPy is great because these big computations, add to arrays, are now implemented under the hood in C, C++, and native code, so it's so much faster than writing that loop in Python. And that's absolutely true. And many of us like to write our machine learning algorithms or our graphics or our vision algorithms in Python, and we might write some code that says add this and multiply this and add this. And I said that, well, that's cool, but this program down here runs a lot faster. Computes the exact same thing, same answer, equal amount of parallelism, runs a lot faster. And why did I make that claim last time? Why do I like, at least if I'm a performance-centric person, maybe not a software engineering person, why do I like this second program a lot more? Yeah. It does, and what are you assuming? I mean, you're assuming that like when I do this math up here, the result is not sent out to memory and then brought back. Right, so you're assuming that the intermediates are stored in registers, basically, which is absolutely true in any instruction sequence. So if you should see this code and go like, oh, look, this code is iterating over the entire array and storing the entire array out to memory and doing that over and over and over again. And this code here is performing one math operation on one element of the array storing it like in a register right next to the ALUs, and then consuming that. And so all the inputs are consumed immediately after they're done, and the only memory traffic we have is the fundamental memory traffic of loading A, B, C, D, and writing E. So this should make you happy. So many of the problems you will see in writing parallel programs on modern machines are absolutely about trying to maximize the arithmetic intensity of these problems, not necessarily finding parallelism. Parallelism was really easy in that problem. Parallelism maybe not so easy in assignment 2. But in that problem there, parallelism was pretty easy. We talked a little bit about some other ways to sort of avoid loading data. And so somebody asked me a question on the website between last class and this one. Was like, how could you avoid a cold miss? Well, that seems a little odd. And so you can think about if you have two threads that share a cache. Well, the first time a thread accesses data, it might be present in the cache because the other thread might have loaded it. And one really good example of that is how we use CUDA shared memory. So if you count, maybe it's a little bit wordsmithing this a little bit, but if you think about a cold miss as a miss the first time a thread accesses a piece of data, well, it could have been brought into the cache from some other thread at that point. Okay, so I'm going to we skip through some of this stuff. And then also last time, I alluded to a problem of artifactual communication, or I differentiated communication that absolutely has to occur to make your program work. And we called that inherent communication. Absolutely, like if we're trying to compute the sum of a bunch of numbers, I have to receive your partial sum from somebody else. Versus communication that just sort of happens because of the ways that are an artifact of the way computers work. So one example that came up was, hey, if I read one value from memory, I get a whole cache line of data from memory. And last time, someone was really clever and said, hey, we can maximize the arithmetic intensity of the grid solver application if we decided not to cut up the grid into these strips, but instead cut up the grid into tiles or boxes. You all remember that? And what was the intuition behind why that was a good idea? Yeah. Exactly. What every processor computes are the number of cells in the block. And what every processor communicates is proportional to the perimeter of the block. And so it makes sense to cut the world up into a bunch of squares. That was our idea. But, and that was an assumption that the only data we had to communicate was the fundamental data, the data that was inherent to the computation. But, so imagine, so now I'm showing you one of those blocks. And so what this block needs is it needs the column to the right, it needs the row to the column to the left, and the row above and below, right? And even if we only need one item to the right or to the left, it might be the case that the actual cost we pay for that might be an entire cache line's worth of data, because communication in one system might actually occur at the granularity of cache lines. So you might devise your algorithm thinking about the inherent communication, and you might be very surprised on a machine that has a high overhead due to artifactual communication. That's one example. Let me give you another example. Let's say we cut up the world into two pieces, and each processor has different information that is responsible for computing. You look at this, you go, great. I'll take my half of the array, you take your half of the array. We're good, right? But it's kind of interesting to think about, well, what happens if processor 1 is writing to like these elements, or the elements in the red box? Processor 2 is writing to the elements in the other half of the red box. They're different elements, but what happens if those elements happen to fall on the same cache line? Like which cache, processor 1's cache or processor 2's cache, is that data actually even sitting in? And so next week we're going to talk about how this situation is resolved. And it actually turns out that most modern machines are going to allow processor 1 to write to the cache line, send it over to processor 2 to write to the cache line, and then send it back to processor 1 to write to the cache line, and so on and so on. So here's a program where if you just looked at it, you would say there should be no communication at all. And there's actually a large amount of communication going on under the hood in a modern machine. So that's why next week we're going to start talking about how shared memory actually works. I'll give you one more example. So now I'm going to use this tiled distribution of work to processors, right? Because we said it was a good idea. Good idea. And if I have a 2D array in C, how do I compute the offset into that array of element ij? I have a 2D, a 2D array, and I essentially have a pointer in C, and I want to compute element ij. How do I compute that? What code would you write? Okay. Yeah, so if I is the row, it would be I times width plus j, right? So what assumption have we made in computing that? We actually made an assumption. We made the assumption that we're going to lay out this 2D grid in memory in a row major fashion. I could have decided to lay it out in column major fashion if I wanted to. Why would that maybe not be a good idea? Because you're assuming that I'm going to iterate over it in row major order. And so if I lay it out in column major order, iterating in row major order would be not very ideal, right? But there are other ways I could lay out that data in memory, right? I don't have to lay it out in row major order like I was drawing here. So my arrows here in this diagram are consecutive memory addresses. So here's a row major layout. My arrows would be going down if I decided to go with a column major layout, right? But I could also actually move to a blocked layout. Now keep in mind that a blocked layout is very different from a blocked decomposition. So in both of these cases, I have tiled what work is assigned to each processor. Both of these examples have exactly the same assignment of work to process. All I'm doing is changing what ij means in the address space. And in this particular scenario, it means that, for example, if my tile size doesn't happen to be a multiple of a cache line size, here all the elements that are assigned to one processor are now going to be consecutive in the address space. So I get perfect spatial locality. Whereas here, I might be iterating through all the elements in the address space, and I might have artifactual communication of data that I didn't actually need. So laying out your data in a manner that is consistent with how you're going to access it can be very important to reduce various forms of artifactual communication. Okay. So who has come to office hours and had to wait? Well, first of all, who has come to office hours? A significant fraction of the class has come to office hours. I highly recommend that you come to office hours. Who has come to office hours and had to stand in line? Was it frustrating? It wasn't frustrating at all. Okay, great. Maybe you had some artifactual learning by some other people asking questions. But I'm always surprised that students, we have office hours and or by appointment on the homepage, right? And I'm always surprised that students aren't emailing me more often for appointments. So let's take an example here. Let's say I have my office hours from 3 to 3:20. Today I have my office hours from 3 to 4, but let's just say it's 3 to 3:20. And the operation that you all have to perform is, the operation is I need to help you with a question. And the steps in this operation are, you move from the Gates Cafe with your fancy latte to my office in Smith Hall. You ask me a question. You have to wait to get access. Some people might be in front of you. And then you get your question answered and you leave, right? So the entire operation is walking to Smith Hall, waiting in line, and then leaving, right? So let's think about what happens if everybody shows up at 3 o'clock, okay? So this is a plot of what students are doing, assuming that it takes 5 minutes to walk to my office from the cafe. There might be some time where you're waiting in line, and last, you get your question answered. And let's just say it takes a finite amount of time to get your question answered every day. So what do you notice in this graph in terms of the amount of time that different students spend at office hours? So how much time does the first student spend at office hours? 10 minutes, right? How much time, let's say, does student 4 spend at office hours? A lot longer than 10 minutes. And why does student, if it took me the same amount of time to answer student 4's question as student 1's question, why did this occur? I mean, it took the same amount of time to walk. It took the same amount of time for me to answer the question. What behavior in the system has occurred? That's right. So if I have an office hours for an hour, and it only takes me 5 minutes to answer a question, right? Is that, yeah, 5 minutes to answer a question, I can service, you know, a fair number of students in that amount of time, 12 students in that, yeah, in that amount of time. So if 12 students arrive at my office hours, it should be possible for everyone to wait, to only spend 10 minutes of their day at office hours, right? So how would I schedule, well, what's the problem, and how would you schedule this computation differently so that we maintained the same throughput and nobody had to wait at all? We could have appointments, and sometimes my TAs, when we were predicting a burst, will say, here's a Google Doc, can you sign up? Right? So what is the problem that has been alleviated by this new scheduling strategy? Yeah. Students can do other things, and really the problem is we had a problem of what in computer science is often called contention. We have a resource that can only provide a service at a fixed rate, and requests were arriving at that resource in a rate higher than what it could service. So even though, let's say, only 12 people come to my office hours, it could have been the case, like I had the throughput to keep up with all the students. But because they all arrived right at the very beginning, it means that some of them wait much, much longer. It'll feel like I have much lower throughput, right? Because to them, when they're waiting for 40 minutes. So if I would have done something like, right, so we said like the time cost changed. You know, with an appointment, I can spread people out, right? Now that can be a little disruptive to me because I'm thrashing during my day, but we can work this out. So contention is a really big problem in that we want to minimize communication. We want to communicate less. But we also want to try and avoid these hot spots, otherwise there can be a big problem, right? So for example, imagine you're doing a reduction, and if you remember from last class, we implemented a reduction in the message passing system by every processor sending a partial sum to one processor, and then that partial sum performing the computation and sending the results back. And it might be the case that if everybody gets done at the same time, there's a whole bunch of network traffic all at the same time, and there's contention for this shared resource, which, you know, for example, if it's Ethernet, might cause exponential backoff or a whole bunch of other problems. Whereas there are alternatives that might alleviate that contention, which is maybe everybody does a combining tree to avoid a hotspot. And for example, you guys thought of that when you were trying to add up a bunch of numbers. The shared work queues that we thought about, or we talked about, are another example of taking a resource that could be contended for and then trying to alleviate that contention. And just as a review question, what would you say is the philosophy behind the way Silk is set up to use these shared work queues, or any system that's using shared work queues? Normally we said, okay, if we want new work, we're going to go synchronize on a global data structure and go grab the work that we need. And the shared work queue approach has a very nice, elegant way of thinking about the problem. And what was that? Was if everybody is busy and no redistribution has to occur, we don't take any cost at all, or very little cost. And why do we take very little cost? So in a shared work queue system, if every queue has work in it, why would I claim that there's no contention? So, every thread will only be interacting with its own queue. And when one thread runs out of work and needs to go get more work to do, we will take some synchronization. It may be contention if a lot of things are running out of work. But why is that okay? Why are we okay with taking that overhead in that situation? Because the alternative is no better than to not do anything. Right, exactly. So it has this nice property of when you don't want to pay anything, you don't pay something. And when it's valuable to pay something, you're willing to pay it. So let me give you a few examples of some contention in CUDA, which can be very surprising to you. I don't think this will come up in your assignment, but here's an example of contention. So here's a situation where I had all the threads in a thread block. This will be definitely in the recitation today. loading a different element so we can load them all into shared memory. Remember this example from class. So all the threads load something to shared memory so that all the data that a thread block needs is now sitting in shared memory. You can now work on this data very locally for the process. So does this code make sense? Is that all threads in a thread block access memory here. All the threads are blocked waiting for all those loads to complete. Right? OK, so now think about CUDA programming. Is we just created a whole bunch of CUDA threads to saturate this core and give it all this latency hiding ability, right? Pretty good. And what did we just do? And the idea of latency hiding is when I'm accessing memory, someone else has something to do to go cover that. So look what this code just did. This code just says everybody's going to access memory at the same time. All those CUDA threads are going to stall, waiting for all these accesses to get sorted out. So in some sense, everybody just showed up for office hours at 3 o'clock, right? And now all this latency hiding is useless because every thread is stalled at this time. So writing code like this is a pretty common thing in CUDA, so it's often actually a good idea to make sure that your thread blocks are small enough that you could have a couple of thread blocks per core. So that when one thread block is like waiting on the sync threads for all its data to come in, all the math can be being performed by threads in another thread block. Because usually all the threads in a block have to sync up together because that was the whole point. So filling a core with one thread block, often a bad idea because you actually create situations of contention on the memory system. Here's another interesting example. Now, a caveat is that I'm not positive that this behavior still exists in the modern GTX 1080 GPUs that you have. So I'm going to talk about something I know previously existed in NVIDIA GPUs. It would be interesting to run this experiment to identify whether or not this is still true. So previously, the way this worked was that shared memory, you probably just think about shared memory as it's just an address space that I can get data out of really fast. And now I want you to think about it like a hardware architect. And the simplest way to think about it as a hardware architect is that shared memory is actually 32 little shared memories, where every lane in the warp, or every vertical column of the shared memory, has the ability to provide one warp, or one lane in a warp, one thread in a warp, one value every clock. So if I say load from shared memory, if every lane accesses its thread ID across the warp, one value is requested from every one of these different banks or every one of these different columns, and the value comes out over this wire back to the ALU. So you can just don't think about it now as one big shared memory. Just think about it as 32 little memories that you can ask for a value in the column. OK, so that sounds pretty good. And by the nature of hardware is that, well, every bank, every column can only provide one value to the ALUs per clock because that's how many wires it has. That's how many bits we can send over that bus. So let's think about, now look at the top right of this slide. Let's think about different access patterns into shared memory. So imagine I have an array in shared memory, and I run the instruction x2 equals a index, and assume that index is just your thread ID in the warp. Okay. So line of code 1 will create this situation, where thread 0 accesses element 0, thread 1 accesses element 1, and so on and so on. So we have every single lane in the warp is accessing a different physical bank in this shared memory, and they can all be carried out in parallel. Now, the other thing I need to tell you is that, well, shared memory has more than 32 items in it, and so you can think about the address space being partitioned across these physical banks of memory mod 32. Right? So if I want to access shared memory offset 32, or byte offset 30, or word offset 32, that would also be serviced by bank 0. So if I was to draw this out, this would be word offset 32. This would be word offset 0, 32, 64, and so on and so on. But remember, the rules of the game is I only have one wire coming out of this thing. So if I run the second piece of code 2, let's say I multiply the value by 3 times index. Well, now thread 0 accesses this bank, thread 1 accesses this bank, thread 2 accesses this bank, and so on and so on. And I still, since 3 is relatively prime with 32, I still have every thread accessing a unique part of this shared memory. And so they can all be carried out in parallel. Does that make sense? Cool. OK. So now look at 3. 3, I just create that line of code. You'll look at it as you're like, oh, that's a memory access, single cycle access to shared memory. Now look, what just happened is now thread 0, 1, 2, 4, thread 0, 2, 4, 6, 8 all need data from bank 0. And these threads need from bank 16, and so on and so on. So even though I have 32 banks of shared memory, only 2 of them actually have data that the threads need. And this could take 16 cycles to get that data out of shared memory. So now you're actually issuing a single instruction, which can take between 1 cycle and 32 or 16 cycles in this case, based on the value and the address that you're requesting. And in all cases, all the data is in shared memory. So it's kind of like a cache miss, but now it's contention for ports on the SRAM itself that is causing you to be off by a factor of 16 or 32 in performance. So it'd be interesting, so they could do a better job if they wanted to randomize the addresses to the banks to make the pathological cases like I just created really hard to create. I don't know if they do that anymore. It would be interesting to write this code and measure it and see if you can figure out what the mapping of shared memory banks to addresses is in modern NVIDIA hardware. OK, so that's a cool example of contention. Let me give you another example. So imagine that I had a physics simulation where I'm trying to compute the gravitation or the forces between a bunch of particles. Like everybody's seen these awesome fluid simulations or scientific simulations. And so imagine I have all these particles, and the particles are my red dots, and the particles are in space, and I want to cut them up I want to figure out what grid cell every particle is in. This is a very common problem in scientific computing. And the reason why I would like to figure out what grid cell every particle is in is, for example, I might want to compute the forces between particles that are right next to each other. And I can do that efficiently if I said that, look, I don't care about interactions greater than radius r, so I'm going to make the grid size the length of my square's radius r, which means that if I care about everything that interacts with this big red dot, it's only in the cells around the cell that I currently am in. So the grid is kind of an acceleration structure for me to figure out what data I have to process. OK, so the name of the game is to say, imagine I have this grid with 16 cells, and I would like to compute a list of what particles are in every grid. Problem make sense? So I'd like to build this data structure here on the right. OK, so what's one way we can do that? Here's one way we can do it, is we can parallelize over these 16 cells. So I can say for every cell C in parallel, for each particle P, if P is within cell C, append P to the cell lists C. Make sense? OK, so let's say that I'm trying to run this computation on a GPU. Let's start thinking about whether or not we've come to a good solution. So first of all, is there parallelism in this problem? Or is there parallelism in my current solution? Yes or no? Yes, it's on the outermost loop here for each cell C in parallel. Makes sense? OK, so that's great. We need parallelism to run efficiently on a GPU. We have parallelism. Are we done? People are shaking their heads. So why are you unsatisfied with this solution? Yes? OK. So you're saying that we have 16 things to do in parallel. And so let's elaborate on that a little bit. So what do you mean every cell is still checking everything? Yep. That's right. But the problem we're trying to solve, I agree completely, the problem we're trying to solve is to build that data structure, not iterate over it. So I'm trying to figure out what particles are in every cell. So I have to figure this out somehow, and I'm proposing, so if this wasn't a parallel program, I might write for every particle, compute what cell it's in, and add it to the list in the appropriate cell. That's my simplest solution. So here I said, well, I changed the order of the loops a little bit. I'm offering up a parallel solution to that problem. Okay. Yeah, but I already wrote this code. What's wrong with it? Like, why am I not done? You told me, I had a homework assignment. In my homework assignment, I was asked to parallelize the construction of a grid, and I did it. Why am I not done? That's true. So it degenerates to the sequence. But let's say they're not. Let's just say there's a good distribution of particles to cells. Yes. Well, I did because I not only claimed, but I. If I ran this on a 2-core CPU, but I'm not. I'm running it on a GPU, and I stated that. So why are you unsatisfied? So you're saying that if we need thousands of things to do in parallel on a modern GPU, well, 16 things to do in parallel is insufficient. So we're not going to fill up the machine. So that's certainly one problem. There's another really big glaring problem here. So I agree. So first of all, this is not enough parallelism to use a modern GPU well. Yeah. So I'm doing 16 times more work in parallel, perfect parallelism. My speed up over this computation, if done sequentially, would be 16. But my speed up over the most obvious sequential version is 0, or is 1, right? So there's kind of two things. One is I don't have enough parallelism to use this GPU. And second of all, I created an algorithm that does 16 times more work to get 16x parallelism. So I completely washed out my benefit, right? OK, so I'm going to take your solution. OK, so yeah, so that's the one we have here. I'm going to take your solution, and I'm going to do this. I'm going to go back to that massively parallel solution that was obvious. I'm going to parallelize over all the particles. I'm going to compute the cell containing P, and I'm going to append it to the list. I'm going to protect that data structure with a lock, because I need to, because now all these threads are banging on the same data structure, right? So we need to protect it. What do you think? Might work. Yeah. The granularity of the lock is extremely large, meaning that I have tens of thousands of CUDA threads all taking the same lock. Agreed. Can you suggest a fix? OK, and I did. Compute cell containing P. Yeah. OK, yeah, so we could move. We could do the obvious thing and say, OK, instead of lock cell lock, we can make 16 of those. And now we have 16 different locks. So our contention for that lock has been reduced by a factor of 16. Might be good. But still, I have like 30,000 CUDA threads contending for 16 locks, and I'm not very happy with this solution. Any other ideas? Yeah. Yeah, we could. And in fact, that's what I tried next. So let's just say, let's just for the sake of diagrams, I could say, you know what, I'm back on this 4-core processor. Let's say I just create 4 data structures. I have every thread make its own private data structure. And then I combine those at the end. So most of the if most of the work is putting the computing what cell I'm in, then most of the work is parallelized, and combining all of these data structures into unioning the lists is kind of like a fancy sum reduction of diff at the very end, right? Very much in the same spirit of how we worked with diff. Now, it's a little bit more costly now because instead of just replicating a floating point value, I'm now replicating this potentially fairly large data structure. But maybe that'll work out. If I have 30,000 CUDA threads, I have to make 30,000 of these data structures. trouble, right? You might be thinking, okay, let's make one data structure per thread block or something like that to reduce the number significantly, and that might work. So let's talk about something slightly different now. So let's talk about this in a 210 kind of way. Let's think about this completely data parallel. And I'm going to try and do this without any locks or anything like that. So let's see here. So let's say that let's first, completely in parallel, we can easily, without actually building the data structure, figure out what cell every particle is in. That's a perfectly parallel operation, right? And that's what I did right here at the top. Right? So every cell, the input is the index of the particle. The red number matches the red number in the diagram. And the black number is what cell it's in. So if a dot is in a box, you'll see that number underneath there. OK. So now let's go ahead and we know that sorting can be done in parallel, right? Like I can give you a library call that sorts everything. So let's go ahead and sort that array by the box that every particle ends up in. So notice that the box, the grid index, is now sorted, and I went ahead and carried along the particle index with it. So the particle index array was all permuted with the sort. Make sense? Okay. So given this array, this step 2 output, can you think of a way to generate this grid of this data structure that I want in parallel? Like, for example, if you look at this array, how many particles fall in box 6? 3. How are you able to do that so quickly? What? It's kind of like a scan. Can you do it without a scan? I want to do an O of 1 time. Or I want to do an O of n work O of 1 time. Where does that part of the data structure start? Where is the start of cell index 6? Sorry? What's that? Yeah, cell 2. How'd you figure that out? You figured it out. How'd you figure it out? Okay, good. And how did you know where the 6 ends? Okay. So you're thinking very serial. Now let's think about it parallel. What happens if I run a computation for every grid element in parallel? How might you figure out whether or not any one element in the list is the start of a list, or any one element in this array is the start of a list? So I could do something where I'm like, wait a minute here. So let's ignore some of these else cases, just because there's some complexity, right? But let's look at this case right here. So if the cell, so if this is thread index, if my neighbor is different from me, I must be the start of a list, right? I must be the start of a list. And if I'm the start of a list, I'm the start of the list of the value that is me. So if I'm containing 6 and I'm the start of a list, well, 6, like you said, better start at 2. And so all of ignore the cell ends, because it's going to be a very similar computation. But the cell starts is, oh, look, item 4, 6, and 9 detect it there, that they are the start of a new list. And obviously, you could do a similar computation to detect if you're the end of a list. So now there's this interesting question of, how do I build a data structure that looks like this here out of this not very compact data structure that has the starting points of all the list elements? And that part I'm not going to tell anybody. Okay? Okay, so the summary of this last lecture and what we've been talking about today is that a lot of the work that you're thinking about is, how am I going to keep things parallel, not introduce a bunch of overhead or 16x extra work, while at the same time minimizing the amount of data that I communicate or situations of contention that can slow me down quite a bit. That is the name of the game in parallel programming. Okay, so any questions about that? I don't think there's going to be too much more discussion of that particular example for reasons that you might be aware of. Okay. So I'd like to go over a few other examples in the remaining time if nobody has any questions about anything we've talked about so far. Should we take a break? Should we relax? Should we stretch? Okay. Okay. So let's go over a few more examples. And I think in these examples, let's actually think about CPUs. It'll be easier to think through these examples as CPU problems. So imagine you have a CPU, kind of like the Gates machines. You have a big pile of cores, 6, 32, 64 cores, and they're all touching the same memory address space, just to keep the things. So let me actually tell you why the heck I use this grid solver example in the first place. And in fact, that grid solver example is a part of a much bigger simulation, a very famous simulation from a couple decades ago that was trying to simulate ocean currents. And the volume of water in the ocean was actually a 3D volume, which means we have a bunch of grids stacked on top of each other. Okay. And so we would use some of the algorithms that we've talked about to solve a heat or a quantity advection equation on these 2D grids, and we'd also do that in 3D in a more advanced thing. And that we would simulate time steps of evolution of the ocean, where every time step would be some delta t. And that if we wanted a high accuracy simulation, well, we'd probably use a very small delta t, run a lot of time steps, and a very large n, very, very high resolution simulation. And just for the sake of completeness, the grid solver is actually, so every major box on this diagram is a big operation on grids. And the grid solver in this application sort of corresponds to these boxes. And so you can think about there being, I have to run this operation on a grid, and then this operation on a grid, and then this operation on a grid. And the users, or the people that made this application, said, look, we could potentially run this operation on half the machine in parallel with this operation on this half the machine. They don't do that. They just decided to make a serial order of all the boxes, and they will parallelize within the boxes. And that's what we've talked about extensively in the class. So, and they used all the techniques that we've talked about. They assigned parts of the grid to processors in this block tile decomposition. They did it statically. They said that, look, there's the same amount of work in every grid, so we can just say that processor 0 has this, processor 1 has this. We never have to touch it again. And the synchronization we have looked at in great detail. We had barriers at the end of the phase. We had locks to protect MyDiff and stuff like that. But there are a few more questions to ask. Like, for example, how much memory do I need? Or what are my working sets? And if you can think back about this problem, there's sort of like 3 working sets that matter a whole lot. I think somebody asked on the website, what is a working set? Well, the working set is the amount of data that you need around at any one point in the computation, because you're going to use it over and over again, and you would like it to fit in some level of the cache. So in this computation, well, the first working set is really the 4 items that you have to average together. And we're going to, any modern computer, that working set clearly would fit in registers. The next working set would be, can I fit 3 rows of the grid in cache, or at least of a tile? Because within a tile, the processor is probably going to iterate in a row major order, and it would like, when it gets back to the front of the first column again, for the previous row to be still in cache. Right? So you'd like actually to be able to keep a couple rows in memory, in the processor's cache. And last, well, at least like a whole plane better fit in memory. Because if we get back to the top here in the next iteration of the solver and we're loading the data off disk or something like that, we're dead. Might as well not even use the parallel machine. So if you remember back from the beginning of this lecture, I said, okay, well, it's pretty simple how we're going to distribute the work on the processors. But we have some options now in our head about how to distribute the addresses, the semantic XYs or IJs, to addresses in the address space. And I gave you 2 examples, row major and sort of tile major, this 4D blocking. And so these folks did this, and they produced these 2 graphs on a parallel machine at the time that had 32 processors. So they ran their code with, like number of processors P, or number of threads was 32. And they produced these 2 graphs, which are pretty interesting, right? And it's really cool when you can produce these graphs in your program because it allows you to performance tune very quickly. So the 3 parts of the stacked bar. The height of the bar is the total amount of time it took one processor to do its job. This crosshatch thing is the time that it's doing useful work. And by useful work, I mean doing computation, doing math. Synchronization is time spent waiting on locks or barriers. And data is time spent waiting on memory or communication from other processors. Okay. So first of all, the simplest question is, the graph on the left is column major order. The graph on the right is tile major order of laying out the data. So the same computations are performed by the same processors. The only difference is what the memory addresses were when we access data. So the first question to you is, and looking at this performance graph, which program is better? The one on the right is better. And the one on the right is better because it takes less time, right? Okay. So the next question then is, well, why is it better? So would you say it's true or false that the program on the left is worse because it has a far worse workload assignment to processors? Like it's a workload imbalance problem, just like problem 1 on assignment 1. Who thinks it's a workload imbalance problem? Nobody. Okay. So yeah, the work is balanced onto the processors. And what about the graph is telling you that? What are you reading off the graph going, okay, I like my workload balance? The busy bars are basically the same. Yep. And the total bars are almost exactly the same. Can anybody explain why the total bars are even smoother than the useful work bars? Yep. Yeah, right, because by the very nature of the problem, we're syncing up all the threads in every iteration of the loop. So if one of them took a far less time than the other, that would be cause for concern. Okay, good. So why is the program on the right better? What does the graph say? The data access time, the black part of the bars, has shrunk tremendously, which means our processors are waiting for data less. And presumably, we're attributing that to the more spatially local layout of the data in memory on this particular machine, which is a pretty old machine. Good. Okay. So does anybody have a sense, and I actually don't have a great answer for you, of the other phenomenon that's kind of interesting in this graph? Yeah. Yeah. And it's it's sort of unclear why. I wouldn't say that there's less, well, there could be less contention, but it also, I don't have a great answer to that question. Like at first I was thinking, okay, well, the bars are smaller because there's less variance in the useful work time, right? Because the top of the useful work plus the gray bars should basically roughly be the same. But that doesn't actually appear to be the case, right? Because, so I actually don't have a good answer to that question. Because I don't know. But it'd be interesting to think about. You could argue that maybe by taking fewer cache misses, like maybe the cache misses were somehow interfering with the barrier traffic or the synchronization traffic. I mean, it's probably some nuanced effect that I have no business explaining. Okay, so our conclusion here is that static assignment was perfectly fine. Using some work queues or some distributed work queues would have been completely overkill for this problem. The 40 blocking is important because it allows a higher cache hit ratio or better utilization of the cache, and that the synchronization cost is definitely important. And in this particular thing, we didn't conclude that from the graph, but it's based on waiting at barriers. Okay, so let's talk about another example. So here's something much more like my simple particle example from earlier in the lecture. But here's like a real burly version that, let's see how this goes. So the simulation, this is not going to be playing, right? Okay, good. So they're simulating these millions, or actually these days billions of particles, and they're simulating the gravitational force between the particles from basically the Big Bang on. So they're trying to understand how the universe evolves based on trying to understand some of the constants or to some of the fundamental laws of physics. So you can kind of see that it starts out very, very uniform. There's a uniform distribution of gas. And as the universe cools, the distribution actually, like the matter in the universe starts to clump, right? Galaxies are forming. And so we're going from something that was fairly uniformly distributed in space to something that is highly non-uniformly distributed in space, as you see from the diagram here. Okay, that's from an example simulation, I think, created at the University of Washington. Okay, so let's talk about this algorithm a little bit. So we have a bunch of particles, and the particles represent stars, or some distribution of mass. And does anybody, what is the equation for, how does gravitational force fall off with distance? 1 over r squared, right? So two bodies will exert a very strong force on each other if they're close. As they go farther away, the forces diminish rapidly with 1 over r squared. So if our algorithm was for every particle, compute the gravitational forces from all other particles to compute the overall force on every particle, and then accelerate it based on that force, what would be the complexity of the algorithm if I had n particles? N squared, right? Okay. So a common optimization that a lot of these simulations make. So first of all, when n is a billion, n squared is not a particularly tractable approach. So what they say is that for particles that are really far away and are going to have really small influence anyway, let's group the mass of a bunch of nearby particles and treat it as like a very massive star far away. So this allows them to take these n squared algorithms down to n log n. And Barnes-Hutt is a kind of a classic algorithm for doing this. These days, there's much more modern and sophisticated ones. But the idea is that if a particle is close to me, I'm going to perform the full gravity computation based on its mass. If a particle is far away from me, I'm going to group a bunch of particles together to compute the aggregate mass and reduce computation by treating that as a single particle far away. So the amount of work that I do is really a function of the distribution of these particles. So if all my particles are clumped together, it'll basically be an n squared computation. If everything is far apart, which actually happens to be true in practice, it's not. So the data structure that they use to represent all these particles is a tree. So particles close to each other will be located in the leaves of the tree, and the interior nodes of the tree correspond to the aggregate mass of all the child particles. So you can think about it as for every particle, find a neighbor, group them together, or find a bunch of neighbors, group them together, and then group those groups, and so on and so on. So if you're familiar with agglomerative clustering, you can think about creating this tree with agglomerative clustering. If you're familiar with graphics and you know about KD trees and bounding volume hierarchies, you could imagine creating this tree with a method like that. Okay. So the idea is that whenever, so let's say we're trying to compute the interactions with the red dot, this particle. And so whenever the mass in a particular region of the subtree, or the ratio of that total mass to the distance of that subtree to the red dot, as soon as that gets small enough, we're going to stop traversing the tree. So the n squared algorithm would be for every dot in the tree, for every other dot, compute the interactions. The algorithm that we're going to say is now for every dot in the tree, start walking down the tree, and whenever the white dot, the interior node, corresponds to a small amount of mass, we're going to stop walking down the tree and treat that as a particle. So for far away things, you're going to stop walking down the tree very quickly. So basically, the rough structure is for every time step, build this tree, and then for every particle, traverse the tree, stopping early, and accumulate all the forces. And in practice, you're going to touch, in practice, about log n nodes. It's the way it works out if you have a fairly uniform distribution of work in the world. Okay, so let's think about parallelizing this particular program. And again, we're going to talk about how are we going to distribute work to processors, and we're going to talk about how we make sure that communication costs are low. So in this particular algorithm, do you think that a static assignment will be sufficient? Let's say I just cut up space into a grid. I do this thing that we did earlier, and we say that every particle in this grid cell run on this processor. Why would that not be a sufficient way to parallelize this particular problem? And if we refer back to the video that we just saw, what did we notice in the video? that suggests that would be a bad idea. So we know the nature of the algorithm is that as time goes on, particles move. And not only do particles move, the statistics of their distribution change pretty dramatically. We go from a uniform distribution to different regions of space will really quickly become more dense or less dense, and so on and so on. So a static assignment, not going to be a good idea. Now, why do you think a dynamic assignment, every time step, let's go ahead and try and figure out how to uniformly distribute work. I'm also claiming that that's probably also not a good idea. And if we think about the video, what did that video tell us about why you don't probably have to solve the workload distribution problem every frame? Because it's the real world. There's some spatial coherence. It takes a while for the universe to evolve. So in the spirit of doing the simplest possible thing, what these folks said is it's perfectly fine to do a static assignment, let the simulation run for a while, detect when you're no longer happy with that many time steps later, and then do another static assignment. So it's like a semi-static approach. So they're not going to take any overhead of a work queue every frame or anything like that, because it's just not necessary. So, but in any one of the frames when you're trying to redistribute the work, how are you going to distribute the work? If I give you this tree, and I ask you to put the same number of particles in every node, or assign the same number of particles every node, what's an algorithm to do that? So, okay, so I'm going to, so your algorithm, let me say it slightly differently, is let's just start with a single thing. And we know that we want n over, let's say we have 32 cores, n over 32 particles per core. So we can just say, okay, are there n over 32 particles in the current node? And if not, let's split it in half. Yeah, that would work pretty well. If you split it in half or something, you might end up with one here and a bunch. And so splitting in half probably wouldn't be sufficient. But I can imagine building the tree that way. And that's exactly how you build the tree. So you're saying there that we would want a tree with 32 nodes. With each thing having. That's right. Okay, and that's a pretty good idea, actually. So another way to say that is if I gave you the tree, you could take the tree that had many more than 32 nodes, and you could walk from the root and find the first subtree that had roughly n over 32 things. And then we could start walking from there and find the next subtree that had the next n over 32 things. And that's exactly how they do it, actually. That's exactly how they do it. And it has some nice properties in that parts of the tree, by the very nature of the tree, particles that are next to each other in space end up being assigned to the same processor. Now, nobody actually said the simplest thing first, which was just take all the particles and randomly assign them to one of the processors, and that would have been perfectly good workload balance, right? So you guys were clever from the very beginning. So one answer would be just give a random number between 0 and 32 to every particle, and that's how it's all going to work out. But your solution maintains the property that particles given to the same processor are going to be very close to each other in space. What I have on the board is not particularly important, but it's an interesting way that we said there wasn't any communication needed to do this assignment. Every processor just takes its processor ID I or P, and then goes and finds the ith chunk of size n over 32, or in this case, w over p. So this can be done completely independently, given that the tree exists without any communication. Okay, cool. Okay, so we've said that we have a really cool way of partitioning the work into very local groups, which we're really happy about. What about how you're going to distribute the nodes to the processors, or the particles to the processors? So one answer could be, let's randomly splat the particles over the processors. One answer could be, let's be more clever. Does anybody have any sense of how you might want to distribute the particles to the processors? Yeah. In terms of laying them out in memory local to the processors. So one thing you could say is this subtree should all be located in the same spot because they're all next to each other. They're going to be interacting. Sounds like a good idea. The only, and that's a perfectly reasonable idea. The only reason why they don't do this is they were really worried about every single time you rebalance the workload, you now need to take all of the data, like petabytes of data across this machine, and shuffle it all around all over the place. So it turns out that they actually don't need to do this. So the reason why I like this example is this is an example where your intuition was exactly correct. We should work really hard to locate data right next to the processors ourselves. So this is a great example of run your code, and the simplest option first sometimes works. So let's think about what happened here. So this is back in this diagram. And as you know, that when I'm processing the red node, I'm going to get all the way to the leaves of a tree for leaves that are next to me. And I'll stop high up in the tree for leaves that are far away. And now imagine doing the same computation for a particle right next to the red node. The particle right next to the red node is going to visit all of the same, more or less, all of the actual same leaves of the same interior nodes and leaves of the tree. It's going to stop roughly in the same spot because all the same math is going to roughly work out. So it turns out that in this particular application, because you have put similar particles on the same processor, they all access roughly the same data. And your caches just bring all that data in, and it just sits there. So even though they wanted to work really hard to make the work distributed really carefully to the various processors, it turns out that just randomly splatting your data across the machine and letting caches do their work turns out to be just fine. So the simple operation that worked just first. So unlike in the last example, the data points here, where data locality and how we laid it out in the address space was absolutely, it was like the thing in performance. In this example, the thing in performance is how you cut the work up into what every processor should be doing. So a completely different strategy. And here's that graph again, where busy work is the crosshatch stuff. Time spent synchronizing is still the gray. And now, again, the black bars are time spent accessing data. And in this case, this cost zones assignment, the smart assignment that you came up with on the fly and people have graduated with PhD theses on, is the sole reason why the black bars have shrunk. Not because we laid the data out well, but because we had really high temporal locality in the probe. What did you ask? Yeah. Oh yeah, you get, the Z ordering. Yeah, we could have laid out the data in many other ways, but the data shows, the performance profile shows, that look how much time we're waiting on memory. So by standard Amdahl's law, if we made the black bar 0, how much faster would we run? You know, maybe 20% faster at best, right? So in this example, you might, if the 20% was really important to you, you would then go chase that with further optimizations. If you were like, gosh, that's going to take 6 months to implement, and it's really only going to give me 20%, you might be like, you know, maybe not worth it. In the earlier case? In the ocean case? So in the ocean case, well, we did do that. We did do that in the ocean case. Sorry? Yeah, we could have done it randomly, and maybe, oh, you're saying why didn't we get really high spatial locality there as well? Okay, now you're asking about big details of the problem. Let me think. Why didn't the caches just absorb all the work? The answer is almost certainly something called false sharing, which I'll tell you about next week. So basically, I can't go back to that deck. But remember how in a 2D blocked layout, a cache line straddled two processors? Two processors wrote to the same cache line. So even though they're writing to different data, under the hood, the machine is having to say, here, processor 1, do your write. OK, now wait, processor 2, do your write, and so on and so on. So I'm making this up. Don't quote me on it, but that would be one reason why making sure that there was no communication. Because here, the data structure that we're touching is all reads. There, we are updating the grid. So all the writes were to my local particles. There was certainly no contention for the writes. In that other example, you're updating the shared grid, and those grid cells might be lying on the same cache lines. I would suspect that's the answer. Okay. Yeah. Okay. I want to discuss one more example. This is probably tiring because it's a fire hose. But I wanted to talk about parallel scan. So how many of you have heard of parallel scan? Okay. So the number of people that have heard of parallel scan is substantially less than the number of people that raise their hand about starting assignment 2. So there's data that doesn't check out. So maybe everybody's only still on part 1 of assignment 2 or something like that. But data parallel scan is almost certainly something that you have seen in 210. And if you haven't seen it, you've probably seen it in problem 2. There are 2 types of scan. An inclusive scan says that the input is an array of numbers, and the output is an operator applied in sequence to that array. So let's say if our operator was sum, then the inclusive scan result of the sequence A0, A1, A2, A3 would be the first element would be A0, because that's the sum of all numbers, including the first element. The second element would be A1 plus A0, because it's the sum of all numbers up until that element, and so on and so on. The exclusive scan version is just the inclusive scan, but not containing the element at that index. So that's why I have the identity for the operator here as the first element. Okay. So first time you might see this, you might be like, well, look, we're adding up all the elements across the array. This is sequential. This is really sequential. And we know that's not the case, right? So what is the work I have to do in a sequential algorithm to compute a scan? O of n, right? And in a sequential algorithm, I guess, it's sequential, so by the very nature, it would take n work. Now, how many of you have seen the parallel version of this scan? So I'm going to give a simple example to start things out, which I'm going to use common sub-expressions in this scan. So in parallel, I'm going to add up all elements right next to each other, the pairs of elements. And then I'm going to continue to use these sub-computations. I'm now going to take, so the first step of this process, I'm going to take adjacent pairs of elements, add them up in parallel. I have a list of millions of elements. I have plenty of parallelism in the machine. Then I can take those 2 partial sums, or every pair of partial sums, and add them up, and so on and so on and so on, right? So what I'm going to draw here is I'm going to say that, well, the next step in the process is I'm taking not adjacent elements, but I'm taking every other partial sum and adding them together, right? And I'm going to continue this until I have, at the very end, if I keep going, I have all the elements added up onto the right-hand side. This is your standard or one scan algorithm. So what is the work that I am performing now? I have a parallel algorithm because every step is really parallel. I lose some parallelism at the end, but I'm not doing much work down here, so I'm not too concerned about it. So how much work is this new algorithm doing? And maybe the first question to ask is, how many steps does it take before it completes? So the first step, add up elements that are separated by 1. The next step, add up elements that are separated by 2. The next step, add up elements that are separated by 4, and so on and so on. So how many steps will this take to complete? Log n. Okay. And how much work is going on here? N log n work. Exactly. So it's actually a very inefficient algorithm compared to the first thing that I told you about. Right? Because there's log n steps. We do roughly n work on a lot of them. Okay. What's the span? It's log n, right? Because there's log n steps. So in your assignment, and in 210, you would have seen a work-efficient parallel scan algorithm. I don't want to go into the details of that algorithm because of the amount of time that I have, and you will study it in detail in your homework. But the point of the work-efficient scan algorithm is that we're going to actually increase the span in exchange for decreasing the work. Right? And so that algorithm will look like this, and that there's a phase 1, an upsweep phase, which kind of does look like the combining tree of the original algorithm in some sense. And then we have a broad, yeah, 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 is 2d, wait, what? Yeah, 2 times d in this, or d to the, d to the 2 to the d. Yeah, which is 2 to the d in this code. Perhaps we should change the variable name. Yeah, perhaps the variable name should be changed. Okay, so, yeah, perhaps the variable name should be changed. Okay. So the work, and I want you to take a look at this. So the work, just take it on faith for right now, and you'll study in your homework. The work is O of n. The span is still O of log n, but how has the constant changed compared to the previous one? So asymptotically, the span is still log n. And in another sense, maybe in your homework, how many CUDA calls are you making? So we have an up and a down, right? So now we have twice as many CUDA calls that we're having to make. Okay. What's the constant on the work itself, actually? Well, if we looked into this algorithm, we could kind of compute it. So there's one math op there. There's one move and one math op there. So depending on how we count, the constant in front of that asymptotic work might be 1, 2, 3, or 4, or something like that, right? That's how many loads and stores we do, or how many math ops we do to get this to work. Okay. So now let's think about running this work-efficient parallel scan on a machine that only has 2 cores. Let's say your netbook or something like that, right? Because you're like, I want to have this parallel algorithm, and so I've learned in 210 that here's an excellent parallel algorithm. It's a famous approach, work-efficient, reasonable span, scales to hundreds of processors really easily. So what do you think about this? You see any issues that might arise with this approach? Does it distribute well onto 2 processors? Well, we don't have the parallelism, but I'm sorry for confusing because I did mention CUDA. Let's think about it not in CUDA anymore, just on a CPU with 2 processors. Okay? Yeah. Right. So in some sense, that would be, like we're taking a big constant overhead. Absolutely. So maybe let's say 4 processors, right? So maybe we can come out with maybe a win on 4 or 8 processors. That's a good observation. I wasn't even thinking about that, is that we increase the constant by a small integer number. And if we only have a small integer number of cores, even with perfect parallelism, we're in bad shape. What about communication here? So does it parallelize well? Yeah, it does parallelize well. Let me go ahead and just divide the data on, okay, this is what core 1 does, and this is what core 2 does. So one thing that's actually quite favorable is the amount of communication between the cores is very little. Very little, actually. But also, the memory access pattern of any one of the cores is also not so good, because you're bouncing all around memory. So your spatial locality in something that's going to be bandwidth bound is quite poor. Quite poor. You could argue that you might sit in cache at the low levels of the upsweep and downsweep, and so it might be okay, but you're still not making very good use out of your cache. So if I wanted to do this on a 2-core processor, how might you start thinking about how you would implement? Okay, so we could solve the left and right, we do the left and right half of the array independently. Okay, but I haven't solved the problem yet. I've solved the problem for the first half of the array. I have the answer. How do we get the answer for the second half of the array? I just need to take the last element, A0 from 6 from the first part of the problem, and push it over here and then do that. Now, I got good parallelism at the beginning. Now I'm sequential in the second half, right? Can I parallelize the second part? How do I do that? Exactly. I can do a sequential scan on elements 0 through 7 on core 1. I can do a sequential scan on elements 8 through 15 on core 2. I actually have the full scan answer now here for the first half of the array. And I could just take the last element, A0, A7, and add it into all these elements on the right. And well, I could divide that computation as well across the two processors. In this example, compared to the previous example I gave you, there was a lot of data touched by processor 1 that now needs to get over to processor 0. But we're kind of assuming this is a shared memory small box now, and all the processors are connected to the same memory system. So there's actually no benefit to trying to keep that locality, right? Because all that data is already out of the cache and in memory anyways. So here's something where it's still O of n. It parallelizes as much as I wanted it to. And my constant is now 1.5. So I'm feeling pretty good about myself. And most likely, my benefit is much, much greater than 1.5 because I basically am striding straight through memory with perfect spatial locality and all that kind of stuff as well. Okay. Good. Okay. So here's an interesting thing. Let's think about, now let's put our CUDA hat back on. Or imagine writing this in SIMD across, I want to do a scan across the lanes of a vector. So I want to do it in AVX instructions, or perhaps I want to do it in CUDA, where I know I'm executing 32 things at once. So here's a piece of CUDA code, and it's actually given to you in your assignment 2, part 3, if you want to use it, that does a scan across a CUDA warp, 32 elements of the CUDA warp. So let's look at what this CUDA code is doing. So this is a function which takes as input an array, and let's just say that array is shared memory array. And every thread has access to its thread ID. This parameter index you should just think of as it's the thread ID. So what is this code actually doing? With a big hint here on the data dependency side. So the first instruction says, if the lane is greater than 1, we're going to, every thread will compute as its own value the element of the array that it owns plus the element of the array to the left of the previous thread. Right? So that's what I'm representing here. Every thread will compute these two. Right? And then the next instruction says, well, if the lane is greater than 2, what do I do next? So after the first instruction, well, this is the original data was the answer for the scan in the first element. And after the first instruction, this is the correct answer for the second element. So what's the next instruction doing? It says, for all threads except the first 2 of them now, add up the partial sum from 2 away to your own, and keep that result. So this should be looking awfully like my nlog n scan implementation, right? So now everybody except the first 2, almost n work, will do another operation. We'll combine these 2 elements here and here, and now I have the segmented scan answer for the first 4 elements. Next instruction, I get the answer for the first 8 elements, and so on and so on. So first of all, how much work am I doing? How much work is this warp doing? It's 5 instructions. Let's just assume that every line of code is an instruction for now, right? It's 5 instructions. How much work is going on? So what's n here? N is 32, because that's the warp size. How much work is occurring in this program to execute this sequence? OK, so it's 32 times 5, right? Because every step is all 32 threads in the warp are execute times 5. So if n is 32, n log n, right? OK. So, and what is the span of this computation? In other words, 5, because that's how long it takes to complete. I have 5 sequential instructions, which is log n. OK. So now let's think about what if I did, instead of, like, you might be like, wait a minute, Kevin, why are you using this work inefficient parallel scan? It's n log n. But now think of what would happen if I implemented the work efficient parallel scan at the warp level. How long would it take? Or in other words, how many instructions would it take me to finish? Because I'd have to do 5 instructions to do the down sweep. And I need another 5 instructions to do the up sweep. So it would take me 10 instructions. maybe even a little bit more with a little bit of the bookkeeping, right? So it would be twice as slow. But I did less work. So what just happened? How do we make sense of this? Why is an algorithm that's n log n taking 5 instructions and an algorithm that's O of n taking 10 instructions? The number of what? You mean the number of lines of code? Because there's no calls of kernel here. This is back-to-back instructions in one function call in CUDA. So my question is, what's going on here? I'm doing less work in more instructions. Yeah. Well, let's think about it this way, and I'll stop after this. Imagine that is this 32? No, this is only 16 elements. But imagine I had a 16 wide warp. Is it advantageous for me at all to run a computation that only does things in 2 of the elements or 4 of the elements? This is divergent execution, right? Like I'm basically masking off almost all of my warp and burning time to run the instructions. So you can maybe make an argument that on some system there might be an energy efficiency benefit. But in terms of the number of instructions I need to get this done, on this particular machine, the minimum granularity of things I do is 32. So anything that saves me work underneath 32 is I'm burning the ALU lane anyways. Okay. Sorry? Well, in this particular case, the total work being done is actually not too relevant because most of the work that's not being done is actually being done anyways because it's masked off. The real relevant thing here is I have a span that's longer by a constant factor in the work efficient algorithm. And since there's no way for me to exploit the work efficiency of the work efficient algorithm, it's not helpful. Okay, so I'll stop there. Okay, I'll stop there. Reminder, we have a review tonight at 7 o'clock in this room.